Hello and welcome to the next installment of DC Circuit Fundamentals. In the previous video, if you had a chance to watch that, we looked at the relationships of voltage, current, and resistance, and power. And now that we're comfortable with Ohm's law, we can examine more than one resistor in a circuit. The first one we're going to look at in this video is what we refer to as the series circuit, where one resistor follows in series after another. Much like a TV series, where one episode follows after the next episode. And if you miss an episode, well, then you have some missing information. And a series circuit is much like that. So let's get started. So we're going to look at the different properties of series circuits. And we'll come up with a set of rules or tenets about series circuits around power, resistance, current, and voltage. When we look at different types of circuits, we can sort of categorize them into three major types. There's the series circuit, where one resistor is in series with another. Then there's a parallel circuit, where resistors are what we call across from each other, or in branches. Finally, there's the combination circuit, which has both series and parallel components. In this module, we're only going to be looking at series circuits and how to solve those relationships. When we think back to our last unit, we learned about resistance, where resistance is the opposition to the flow of electric current due to a material's physical properties. This is based around what's going on in the valence shell and how easily it is to push or move an electron out of its orbit along a conductive medium. During our examination, we looked at the schematic symbol for a resistor. It's basically just a generic piece of resistive material, and the line's a little wiggly or long to make it look like a longer piece of material. So keeping that in mind, that just any conductive material or conductor can be just a piece of resistive material, we can then sort of examine a series relationship. So let's look at just a piece of resistive material, such as a piece of wire. And let's suppose that this piece of wire has a high resistance. So we'll just represent that by a tube or just a length of material. And let's say this piece of material has 100 ohms worth of resistance. So the resistance of the material is due to its length, its cross-sectional area, as well as the material type itself. And as stated in this example, let's say it's 100 ohms. If I take that piece of material and I cut it exactly in half, so previously it had 100 ohms, how much resistance would each half have? Well, each half would have 50 ohms worth of resistance if the resistance is due to the material. So if an electron had to go through the single piece, the 100 ohms, it would have to go through 100 ohms worth of opposition. If the same electron had to now go through the two halves, it would still have to overcome 100 ohms worth of resistance, 50 in the first half and 50 ohms in the second half. Now let's suppose that we cut those two pieces into halves again. So now I have quarters. So the 100 ohms is now cut into 4 equal pieces. How much resistance does each piece have? Well, 100 divided by 4, each piece would now have 25 ohms worth of opposition. Now again, the electron, if it had to go through all 4 pieces, would still have to overcome 25 plus 25 plus 25 plus 25, or 100 ohms worth of opposition. And this is the principle behind a series circuit. The electron has to go through different resistive pieces, but the overall opposition is the sum of all the individual pieces. Let's take a look at how resistors add in series. If I should have a 10 ohm resistor, then my current flow, or my flow of electrons, have to overcome 10 ohms worth of opposition. If I should add a second resistor of equal value in series, then my electrons have to first go through 10 ohms of opposition and then another 10 ohms of opposition, for a total opposition of 20 ohms. And if I should add a third one in series, then my current flow has to overcome 30 ohms of opposition. So when it comes to series resistance, resistance adds directly, where all the resistances in series add up to the sum, the total sum. We use subscripts in order to keep track of different locations, so that we know exactly which part, piece, or value we're looking at any given time for a given problem. So R1 would be resistor 1, R2, resistor 2, R3, resistor 3, R4, resistor 4, R5, and resistor 5. And in this particular example, RT represents the total resistance for the entire circuit. Each location, you usually keep the same script. So for resistor 1, it would have voltage 1, it would have current 1, it would have power 1. So the 1 allows us to know that we're talking about the first location. And then the 2, the second location, the third, the 3 location, and so on and so forth. The subscripts just let us keep track of where we are and what values we're talking about in which location. Current is the flow of electrical charge past a given point through a conductive medium. If we follow the current here, you can see that there is only one path for the current to flow, where the current has to go through each successive resistor. Again, this particular diagram is using electron flow, not conventional current flow. Here we have a conductive path, or a closed circuit, going from, in this case with electron flow, from the negative of the power supply to the positive of the power supply. Since the conductor medium, or the circuit, is full of electrons, as you put one electron into the circuit, it pushes all the rest in front of it around, so that when one electron goes in, one comes out immediately, because it pushes the entire length of electrons along the conductive path. Thus, the current is the same throughout the entire circuit. The current is determined by the overall resistance, the sum of the resistors. So we say that in a series circuit, current is common to all series components. So that the current in resistor 1 is the same as the current in resistor 2, which is same in 3, 4, and 5. The total current is the same as the current through all the resistors. Current is common. In a purely series circuit, there is only one path for the current to flow. That's part of the reason why the current is the same through all series resistors. Here there is only one path from A to B. So if you're to take your finger and trace it from A to B, there is no other place for your finger to wander off. There is just one path. Here again, there is only one path for electrons to flow from A to B. Same again. It looks different, but there's still only one pathway for the electrons to flow. Doesn't matter of the orientation. If you trace your finger from A to B, there is only one path. Here again, looks different, but there is only one path, which makes current common to all the series components. Since there is only one path, the electrons must flow through each of the resistors. This limits the flow of the current. Since it has to go through all the resistors, the resistance is equal to the sum of the individual resistances, where the total resistance, RT, is equal to however many resistors there are in a series circuit. We sometimes abbreviate this formula to RT is equal to sigma R, where we use the Greek symbol sigma in mathematics to symbolize the sum of. So anytime you see the Greek letter sigma, it means the sum of, or the total sum. So for an example, here we have a simple series circuit containing three resistors: a 20 ohm, a 30 ohm, and a 50 ohm resistor. The electrons are forced from the negative of the power supply past point A, where they have to go through R1 of 20 ohms, past point B, where they then have to go through R2 of 30 ohms, past point C, where they have to go through R3 of 50 ohms. Then, after point D, the electrons can make their way back to the positive side of the power supply. The electrons are forced through 20, 30, and 50 ohms, for a total of 100 ohms of opposition. When we're adding this up, RT is equal to the sum of the resistors, where 100 ohms is equal to 20 plus 30 plus 50. So you can pause the video here for a minute, but what I want you to do is calculate the total circuit resistance and the circuit current for this simple series circuit. I'll give you a minute to work on that. Starting this problem, we would often write down the formula. RT is equal to either sigma R, or you can expand it. RT is equal to R1 plus R2 plus R3, R4 plus R5 plus R6, because there are 6 resistors in series. We would then take the sum of the 88 ohms, 47 ohms, 18 ohms, 12 ohms, 35 and 75 ohms, respectively. This would give us a total resistance of 275 ohms. So now we have the total circuit resistance. This is the total opposition that the electrons will see as they leave the power supply of 220 volts. Since we know what the power supply is, E, and we know what the total opposition is, RT, we can now calculate the total current, where IT is equal to ET over RT. We fill in the values, 220 volts over 275 ohms. We end up with 800 milliamps. So far, we know that current is common in a series circuit. And we also now know that resistance adds in series, where the total resistance is the sum of the individual resistances in series. Now when we look at voltage, we can use something that's called Kirchoff's voltage law. Kirchoff noted that the individual voltage drops across each resistor will add up to the power supply, or the voltage around any one current loop is equal to 0, is how he actually stated it. So that the total voltage is equal to the individual voltages within the circuit. So the voltage at R1 plus the voltage at R2 and the voltage of R3 will equal the power supply. The system must be balanced. And this is an excellent way that we can check our work. Let's look into this a little further. So here we have our circuit again of R1 of 20 ohms, R2 of 30 ohms, and R3 of 50 ohms. That gives us a total resistance of 100 ohms. When we apply 120 volts to the source, that gives us a current of 1.2 amps. Since the current is common to R1, R2, and R3, they all have the same current of 1.2 amps. We now have a current at each of those locations. Using IR, we can calculate the voltage for each of those locations, where the voltage at 1 is equal to the current times R1. Now I just use the subscript RT, or IT rather, because it's the same current, so it's the total current. So I used IT for the current. So IT times R1, 1.2 amps times 20 ohms, that's going to give us 24 volts. You will notice now that I'm using V, the letter V instead of E. E is for an electromotive force, or some sort of source or generation. I'm putting voltage into a circuit. It's a supply. Now, for the individual voltage drops, because I will have a difference in charge across each of the resistors, I'm going to use a slightly different letter. I'm going to use V to represent those voltage drops. So that way I know it's a loss and not something where I'm putting voltage in or a gain. We can do the same thing. ITR2 is going to give us 36 volts across that location between B and C. And then if we take a look at the voltage across R3, it's 1.2 amps times 50 ohms, or we're going to end up with 60 volts across R3, or between points C and D. And sure enough, if we add the voltages of V1, V2, and V3, it adds up to the source of 120 volts. As I mentioned before, there's a couple ways to state Kirchoff's voltage law. One is that the applied voltage must equal the sum of all the voltage drops, where 120 volts will equal V1 plus V2 plus V3 in this example. And it does when we calculated out the voltage drops in the previous slide. 24, 36, and 60 added up to 120 volts. You may also hear Kirchoff's voltage law stated a different way, where the applied voltage minus each of the voltage drops must equal 0. We also sometimes state it as the sum of voltages around any one current loop must equal 0. In that case, the voltage source is a gain, 120 volts, and then we're going to lose 24, we're going to lose 36, we're going to lose 60. So that when I add those all up together, it turns out to be balanced, or 0 volts. Kirchoff's voltage law is a very powerful tool in seeing or checking your work to see if it's correct, because the system must be balanced. Let's do another little sample problem. Here, I've got three resistors in series, a 30, a 25, and a 20. We're going to apply 120 volts to the circuit, so that our total resistance is 30 plus 25 plus 20, or 75 ohms. We can now have, or calculate, the circuit current, because we have RT, and we know what our source is, ET. IT is equal to ET over RT, or 120 volts over 75 ohms, which gives us 1.6 amps of current in the circuit. Again, current is common in a series circuit. So R1 will have 1.6 amps, R2 will have 1.6 amps, and R3 will have 1.6 amps. So calculating the voltage across R1, V1 is equal to ITR1, or 1.6 amps times 30 ohms. It'll give us 48 volts at that location. V2, 1.6 amps times 25 will give us 40 volts at the second location. V3 ITR3 will give us 32 volts at that location. Now we calculated the current, and we use a calculated current to help us calculate the voltage. How do we know that those voltage calculations are correct? Well, we can use Kirchoff's voltage law, where does 120 volts equal the sum of the three individual voltages? It sure does. When you add 24 and 36 and 60, you end up back at 120 volts. We can use Kirchoff's voltage law in other ways to help us find values that we don't have. Here we have a circuit with three resistors in series. Across the entire rail, we have 120 volts. So our source voltage is 120 volts. The voltage across the first resistor is 32 volts, and the voltage across the second resistor is 46. So what would be the unknown voltage across R3, or VR3? Well, we know from Kirchoff's voltage law that the three voltages have to add up to 120 volts. So if we take those values and plug them in, we can take 120 volts and subtract the 32 and subtract the 46, and whatever's left over has to be the voltage across R3. And when we do that, we find out that the voltage of R3 is 42 volts. But what about power? Well, when we went back and looked at a single resistor, once current started flowing in a circuit, the resistor started generating some heat. And that conversion of electrical energy into heat energy is what we call true power. And it's measured in watts. We calculated the current, and in this case 4 amps. And then using that current, we could find or use any of our three power formulas to calculate the power dissipated in the resistor. We could have used PEI and ended up with 480 watts. Or we could use P is equal to I squared R, or E squared over R, and also equally gotten the same answer of 480 watts. All of these formulas still hold true. The only thing you have to remember is that in a series circuit, you can only use values for a given location. So for any given resistor, I have to use the current, voltage, and resistance for that specific location. Let's do an example. Let's take a look. Here we are back to our circuit that we worked on before, where we had 30 ohms, 25, and 20 ohms. We had an RT of 75 ohms, and we had calculated a current of 1.6 amps. And when we did this problem before, we calculated the three voltages to be 48, 40, and 32. Now, when we calculate the power, if we're calculating the power at resistor 1, or P1, we have to use the voltage at resistor 1 and multiply that by the current. Again, the current is common, so everyone's going to have the same current. We're calculating the power at location 2. We have to use the values of location 2, as well as the power at resistor 3. We can only use the values of location 3. And when we do those, we multiply them out, we end up with 76.8 watts for P1, 64 watts for P2, and 51.2 watts for the power at resistor 3. The total power of the circuit, the power that the supply must be able to deliver, PT, total power, is equal to ET/IT. So if we take our 120 volts, or ET, and multiply by our current 1.6 amps, we end up with 192 watts. But if we look at the power of 1 and the power of 2 and the power of resistor 3, and we add those up, we find that the sum of the individual powers here also equals 192 watts. So in a series circuit, the total power is equal to the sum of the individual powers. This is also another good thing that we can use to check our work at the end. PT is equal to the sum of P, where the total power dissipated by the circuit is equal to the sum of the individual powers. Or PT is also equal to ET/IT, as it always has been for us since we started. Again, I encourage you to pause the video for a moment to work out the values. Here's the circuit we were working on earlier, where we found the RT and IT for this particular circuit. At this point, I encourage you to go through and calculate each of the individual voltages. After you calculate all the voltages, carry on and calculate all of the individual powers. So pause the video here until you've had enough time to work through, and then check your answers against the ones that I'm about to give you. RT, as before, is 275 ohms, which gave us 800 milliamps, or 0.8 of an amp. These are the values for the first 3 resistors, for their voltage, the voltage of the next 3 resistors, the powers of the first 3 resistors, and then the powers of the last 3 resistors. Our total voltage is 220 volts. Our total power is 176 watts. If you add all the individual voltages up, you should come up with 220. And if you do the sum of all the individual powers, you should come up with 176. So, for series circuits, we learned that the current is common anywhere along the circuit, where the total current is equal to the current at any given resistance. The total opposition, or the total resistance, is equal to the sum of the individual resistances in series. Next, we learn Kirchoff's voltage law, where the total voltage must equal the sum of the individual voltages dropped at each resistor. The final tenet for series circuits is power. Power adds in a series circuit. The total power is equal to the sum of the individual powers. So, to recap, series circuits, current is common, resistance adds, voltage adds, and powers always add. This concludes this unit on series circuits.